So I'm filming this a couple days later after my last video for part one. Just had a busy week with work, and day 10 part two actually took me a while to figure out. I took like 3 different takes to. I started recording, and then I realized how much more complex part two is than part one, and it took a few different approaches for me to figure out the ultimate the 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 solve for that. So I'm just going to give you a run through of what I did. So essentially here, this first part is pretty simple. You just have to, they give you basically the order, and you are connecting them in that chain, and that's it, pretty straightforward. But as soon as they introduce this other element of it where there are many different possible arrangements, it gets exponentially more complex. So just to give you an illustration here, you can model this as a graph. So I have this DAG here, this acyclic graph. And if we have adapter 0 in this example input, 0 can go to 1, 1 can go to 4, and then from here there's 3 options because you can go between 1 and 3 joltages. So 4 can go to 5, 6, or 7. If it goes to 5, it can then go to 6, which can then only go to 7. If it goes to 5, it can also skip over straight to 7. So they're asking us essentially to compute all of the possible paths through this graph. And initially, the approach I took was just to recurse and do a depth first search of this graph, and that worked for the sample input. This really wasn't that hard to parse through and figure out. If I recurse down through here, the recursion essentially makes its way all the way down here and then returns back up the possible number of paths. You basically start with this base case. There's only one possible path there. There's still only one possible path, one possible path, one possible path, and now there's 2 here, and then you just recurse back upward, and then you get the number of distinct paths through this graph. Well, that works fine for an input of say 30 numbers. That doesn't add too much overhead computationally. But as soon as they give you this example input, which is really only like 90 something numbers, the graph can get extremely complex. And so my recursive solution worked pretty quickly for the example input, but then as soon as I gave it this more complex problem 2 input, I let it compute for 20 minutes and it still didn't have an answer. So what I did was I did this thing called dynamic programming, which uses recursion, but it also saves the result at each level. So the way that this works, let me talk you through it. Here's my day 10 part 2 test. And then I have this joltage graph. Here's the abstraction that I made here. It's this graph. It's a DAG called the joltage graph, and then it has a map of nodes to their children. So the children would be right here. The graph would have a 4, and then it would have a set of these children here. And what I did was, here, like for my distinct paths method, this is recursive. And so it goes through, and if we basically pass in the source, which is, in this case, the starting node, we want the number of distinct paths between 0 and this 19 node here. And what this does is it goes through and recurses through the children until it does a depth first search, until it gets to this destination node, and then it returns 1 up there. So that the idea here is that the base case is that the distance between the destination node and itself, there's only one path from the destination node to itself. And then as we recurse out, there's going to be more and more paths to this destination node. And the critical thing that I did here that made it run versus spin for 20 minutes is this visited map of nodes that I've visited and the number of paths to this node. So So what I did was, if the visited does not contain this source key, the current node, then compute the paths to the children. But if it does contain it, just return what we've already computed. And that's critical because you might have a really complex graph with multiple paths to this node. So for example, this 7 node, there are 1, 2, 3 different paths to it. But we already know that from the 7 node to the 19, there's only really 2 paths here. And so this 7 node, instead of recomputing these paths 3 different times when we get to it, we can just return up those 2 distinct paths that we already know about and we have cached for this node. And so that actually that skips over a lot of computation. That's kind of the nature of dynamic programming, is that you store the results that you compute of these subproblems, and then you return those back up through the recursive stack. And so this was able to run pretty quickly. I mean, I got a result almost instantly versus having it run for 20 minutes and keep recomputing these things that it already had computed. So, so essentially, like, to break down this class, I pass in this list of adapters that I parsed out like I did in part 1. It maps it into a distinct entry in this map for the node and then the set of child nodes, and then it computes the valid adapters. So these are adapters that are in the input that are they're greater than the value. So in this case, it would be like anything that, like, 1, the valid adapters would be 2, 3, and 4. And so the get valid adapters would return any adapters in the list that are between 2 and 4 inclusive. And that's how that maps the possible children for this node. And it returns a set of those. And then I just, like I said, I did this distinct paths, which is the recursive dynamic programming approach that caches the result of the computation for the distinct paths. And that's my class here. So this is going to be a quicker video because it did take a few different approaches to solve this, but it's really not too bad once you figure out that caching. The caching is really the critical piece of that, caching those results that you get. So I'm going to wrap this up and then I'll start day 11. I'm excited for that one. So I'll see you in the next one.